Thank you. So I'm talking about two NESP projects, 2.3.1, which was started by Katerina Fabricius, and project 5.3, which I've led following on from that work. And looking more at the marine end of the water quality story here. So, as probably everyone knows, each year the Great Barrier Reef Marine Park Authority and Queensland Government, through Reef Plan, put out a report on the condition of the Great Barrier Reef and its catchments to help monitor progress against the plan and see how things are changing. Currently, on the marine side, we have three sets of indices, one looking at seagrass communities and their condition, one looking at coral based on coral marine monitoring, and one for water quality, which is really one of the main levers that we can pull, trying to manage water quality better in order to improve the health of coral and seagrass habitats. At present, water quality is the odd one out in that it only includes two indicators feeding into that index, and those are Secchi depth and chlorophyll. And the problem with those is that they're a little bit abstract, and they don't necessarily, they relate to water quality, but they can be a little bit hard to relate to ecological outcomes. So the goal of this project was really to develop a new water quality indicator that better reflected ecological outcomes and the ecological requirements of coral and seagrass habitats in particular. As we know, light is really important for corals and for seagrasses. It drives photosynthesis and ultimately drives growth and recovery from disturbances. And the amount of light that gets to a habitat sitting at some depth in the water depends on the amount of light at the surface, but also how much is absorbed as it makes its way through the water due to the water quality, the constituents such as phytoplankton and suspended sediments that are in the water. And that the signature of that light changes as you go further down, and certain colours are absorbed higher in the water column than others. So the first step in putting together a new indicator based on light was to look at, well, what are the light requirements of corals and seagrasses, and are they responding to light variations over the course of each day, or is it really the integrated daily light dose that they get that makes a difference? And so in project 2.3.1, Katerina and her team did a whole series of experiments in the sea simulator looking at the light requirements for corals, both as adults and in their juvenile stages, and published a few papers out of that. One of the main findings, though, was that on the whole, the growth of corals is more related to the integrated daily light dose and doesn't respond very strongly to subdaily variations. And we were generally seeing consistently that the response levelled out at a certain optimal daily light dose, and above that you didn't see much additional benefit, and that's typically within the range of around 14 to 16 moles per square metre per day of photons across a few different species. We also reviewed the seagrass light response literature, and although different seagrass species can tolerate a range of different light levels, and you'll find seagrasses well below what we might consider the optimal light for maximum growth, that threshold of 14 to 16 moles per square metre per day is not too far off the maximum that's likely to be able to be used for additional photosynthesis there as well. So the next step, of course, is if we're going to be using light or photosynthetically active radiation, which is that set of wavelengths, that portion of the total light spectrum which is used by plants for photosynthesis and by coral symbionts, we need a way to estimate what that is at the depth of benthic habitats where they occur. And we needed that to be cost efficient and something that can be routinely monitored across the whole Great Barrier Reef. So our PhD student Tess Canto and Lachlan McKenna developed an algorithm to estimate benthic light from satellite ocean colour observations, basically combining the known depth of the water from maps of the Great Barrier Reef bathymetry with ocean colour estimates of light attenuation at each of several different wavelengths that can be obtained every day on a grid scale of about 1 square kilometre across the whole Great Barrier Reef, to come up with a method to calculate photosynthetically active radiation at any given depth below the surface, including the depth of the benthos. So this slide is just sort of illustrating that. We combine the map of bathymetry of the Great Barrier Reef with what we know about light attenuation at each wavelength and extrapolate the surface light down to estimate the amount of light that's received at the bottom in each pixel. And that was the first step and the basis of our new indicator. But that amount of light at the bottom doesn't immediately tell us until you combine it with the information about the light requirements of corals and seagrasses. It doesn't immediately tell us how those variations in water quality are affecting ecological condition. So we took those maps on the right, which we can produce for every day with some gaps with cloud cover, and calculated a light stress index which for each pixel, which is effectively the amount of stress that photosynthetic organisms in that pixel would experience due to having light that is not necessarily too low for them to survive, but too low for optimal photosynthesis. If light's above that threshold, they're not going to be experiencing any additional benefit, but if it's below that threshold, they'll be under a certain amount of stress. So that gives us one map, but it still doesn't quite tell us the answer, because naturally there are areas of the Great Barrier Reef Marine Park which are naturally deep and won't be getting very much light to the bottom for that reason. And there are areas near the mouths of rivers which may be naturally turbid and won't be getting very much light in any conditions due to tidal resuspension of sediments and so forth. So we didn't want to penalise areas which are naturally deeper and so forth, and therefore getting less light. So what we did is we took these light stress maps and compared them with the light stress under optimal conditions for each pixel. And for that optimal water quality condition, we simply took the conditions that were the 95th percentile best conditions experienced over a period of 10 years at that time of year in that spot. And that allows us to calculate a relative light stress map across the whole Great Barrier Reef on each day. And if we simply add that up over a period that we're interested in, whether it's a season or a year, we get a measure of chronic light stress due to variations in water quality. And we can see that that can vary quite a lot from year to year depending on the events that are experienced. Things like changes in river flow and cyclones passing over have a very noticeable effect over wide areas of the Great Barrier Reef. So there we're comparing 2011, which had Cyclone Yassi and a couple of other cyclones really stirring things up and bringing big river loads, with a relatively dry year where conditions were better. In order to be able to report changes from year to year, we can aggregate this for each NRM region and water body and get a time series to see how that water quality indicator is varying over time. And that this is what this is showing here. Now, as we move from the top to the bottom of that diagram, we're seeing the gradient from Cape York in the north to the Burnett Mary region in the south, and we see that the water quality indicator based on Benthic PAR is generally showing that water quality is consistently tending to be better up near Cape York than in the south, as you might expect. And as we move from left to right in that diagram, we see the gradient from much more variable coastal conditions to much more consistent conditions offshore. But we do see in the coastal and to some extent in the mid-shelf region variations in this indicator which reflect year-to-year variations in river flow in particular, but also other factors that impact water quality. Just taking it back to our goal of making sure it's ecologically relevant, we've done some work with Catherine Collier's team to relate that Benthic light data product, which is incidentally available on eAtlas for the period from 2002 up to fairly recently, to the distribution and composition of seagrass communities, and find that it's a reasonably good predictor of seagrasses. And I've done some work with Angus Thompson looking at whether variations in this new index predict variations in coral community health. Angus has developed an index called the Coral Index, which measures that coral community health. And if obviously that responds very strongly to acute stresses like bleaching events and COTS outbreaks, but if you account for those, there's still some variation left. And these graphs are showing how much of that remaining variation is accounted for by our new Benthic PAR index. And we do find that in some regions, particularly those regions where we do have significant year-to-year variations in water quality, the Benthic PAR index accounts for quite a lot of that remaining variation in coral index. In other areas, particularly where there's not so much variation in water quality, and Benthic PAR is good all year round, then it doesn't explain the additional differences. Just one last slide showing that the benthic PAR index by region does respond quite strongly to variations in river sediment and nitrogen loads near shore, but we're also seeing a signal in mid-shelf waters, so that influence from rivers does extend out a little beyond those immediate near shore reefs. And I'll also mention that it correlates reasonably well with the existing water quality indices, but much more strongly with chlorophyll than with sediment. So that again highlights the importance of keeping control of nutrients, including the nutrients that are brought in with sediments, and not only the sediments themselves. So just in summary, we've produced a number of data products which are available through eAtlas, including satellite-derived benthic PAR estimates, PAR at 8 metre depth, maps of light stress and spectrally resolved light extinction coefficients, which are all available. The new light stress index is based on the habitat requirements of corals and seagrasses, and it tracks not just variations in water quality, but ecologically relevant variations in water quality because it relates to those ecological requirements. We have used it to explain and help to predict changes in seagrass distribution and coral health. And the lonely poster outside is talking about an application modelling how seagrass distribution might improve if land management practices are improved. And we'd like to recommend that this new indicator, light stress, is incorporated in future reporting, perhaps alongside the existing metrics, to help increase the confidence and the ecological relevance of that water quality index. So thank you very much. And again, I'd really like to acknowledge my colleagues who have contributed to this.